Hi everyone, this is the screencast on 7C bond polarity. I just realized my PowerPoint says unit 5. That is not true. Ignore that. So you should have a paper note copy in front of you that's titled 7C bond polarity. If you don't, please find it. If for some reason, again, you can't find it, there is an online copy linked on Canvas. There's two types of polarity, okay? There is polar and non-polar bonds. If two atoms have the same or very, very similar electronegativity, they form a covalent bond where they share their electrons evenly, okay? So they're nice and happy. And think of tug of war, okay? The two atoms, they have equal strength, all right? This is what we call a non-polar covalent bond, all right? If two atoms do not have the same electronegativity, or they have a large enough difference, one atom has a stronger pull on the electrons than the other, those electrons are going to be shared unequally. This is what we call a polar bond. So again, think back to tug of war example. One atom is a lot stronger, okay? Think about it as being like a bodybuilder, all right? The other atom, pretty strong, okay? Works out at the gym, but is not able to keep up with the bodybuilder. And so the bodybuilder is able to get a higher, a stronger pull on that rope, okay? We also have an ionic bond, and ionic bond is when you have a bodybuilder competing against someone who has never worked out in the day of their life, has absolutely no muscle mass, okay? So that bodybuilder is going to be able to pull once and get all of the electrons, all right? So that's an ionic bond. So we have non-polar, polar, and then we also have ionic in our polarity scale. But right now we're just gonna be focusing on non-polar and polar. So when we have a polar bond, okay, we end up with partial charges, all right? The electrons are pulled to a certain direction, and we use a Greek letter, delta, to show a partial charge, okay? This is the lowercase delta, okay? I describe it as a S with a tail. So you start by drawing an S, and then you just loop the tail, okay? But we use that to show partial charge. And it tells us, okay, what atom has more electrons and which atom has less of the electron. So the less electronegative atom, okay, the one that's not really able to keep up, is going to have a partial positive charge, okay, because it kind of has a less of a hold or a weaker hold on that electron. It has less of that negative electron. The more electronegative atom is going to have a partial negative charge. So a partial positive would look like this. Okay, we put a little plus sign. Partial negative would look like that. We put a little negative sign on our partial charge. Okay. So when you see these partial charges, this is an automatic giveaway. You have a polar bond. So here's some examples. So here we have H2O, okay? And just an FYI, the way that these compounds are shaped is a little hint to what we will be talking about next. So H2O, okay, hydrogen, not very electronegative. Oxygen, pretty electronegative. So oxygen has a stronger pull. Oxygen is the bodybuilder in this case. It is kind of winning this tug-of-war game right now. Hydrogen is still pretty strong though, all right? Don't give up on hydrogen. but it's not winning, okay? It's still in the game, still playing tug of war, it's just not winning the game. So then we also have nitrogen and hydrogen have these partial charges as well. Carbon and chlorine are also have partial charges, but we haven't placed them yet. Okay, so think back to our periodic trends unit, okay? Think about the trend of electronegativity. If you do not remember, if you still have your notes, go look at your notes on how electronegativity increases in the periodic table. We're going to go ahead and draw partial charges, all right? So electronegativity increases as you move up and to the right of the periodic table. Chlorine is more electronegative than carbon. So all of my chlorines are going to have these partial negative charges. Well, carbon has a partial positive charge. Okay? All right, so that's what it would look like with you putting your own partial charges. All right, so now we're going to talk about actually calculating polarity. So first thing I want you to do, hopefully these are out. There are these green laminated polarity handouts. We have used these before when we talked about types of bonds. Okay, if these are not out, there is a copy on Canvas under the references modules. I want you to pull that up. The really important part here is the Pauling electronegativity values. Okay, so these are the really important parts that we're going to be using. You are also going to need a calculator. Okay, if you are really good at subtraction, awesome. Maybe you don't need a calculator, but I would like you to get a calculator just in case. Okay, so with calculating the electronegativity difference, we always start with the larger number, okay? We're never gonna have a negative number, okay? No negative numbers. All right, so in this case, fluorine is more electronegative than oxygen. So fluorine's value is 4, okay, minus 3.5. That is equal to 0.5. Now, electronegativity doesn't have units, okay, so you don't need to worry about units here. So we have a difference of 0.5. On your handout, it also gives you the values, okay, of what is polar, what is nonpolar, all right? And notice, okay, 0.4 is nonpolar, 0.41 is polar. That's gonna be important when you do your practice. So I have a difference of 0.5, which means my bond of oxygen and fluorine is polar. All right. So next, we're going to look at carbon and hydrogen. So carbon is more electronegative than hydrogen, so I'm going to start with carbon. Carbon has a value of 2.5. Hydrogen has a value of 2.1. That equals 0.4. All right, again, this is where the kind of number scale becomes really important, because if you look at your handout, okay, 0.4 is nonpolar. So we're going to write nonpolar, okay? So with polar bonds, we also have something called a dipole moment. This is going to be very important when we get to the next topic in this unit. But we use arrows to represent dipole moments, okay? There are some really cool technology that can show 3D diagrams of dipole moments. Those are really cool to see. However, we are a high school, we are not using 3D diagrams with polar bonds, so we're going to use these arrows, which they've used for a very long time. So the arrows are special because they have these little tails on them, all right? And the arrow starts at the partial positive charge and it points towards the partial negative charge, okay? So that's really important because the tail looks like a plus sign, all right? So the tail looks like a plus sign. So your plus sign should be at the less electronegative atom, the one with the partial charge, okay? Another aspect of these dipole arrows that are important is that the length of the arrow tells us how polar the bond is, okay? I think this is known as a vector, all right, which you'll talk about more in physics. But the length of the arrow tells us how polar the bond is. Now, I don't want you to worry about that, okay? Do not worry about the length, all right? I'm not going to be looking at how long the arrow is. I will be looking at, is the arrow starting at the least electronegative atom, the one that has the partial positive charge, and is it ending at the more electronegative atom? All right, we are going to do an example. Your homework is going to basically be what we're doing in this example. So we are going to draw the Lewis dot structure of CH2O. So remember, first we have to find out what our magic number is. So how many valence electrons we have. So carbon has 4, hydrogen has 1, I have 2 hydrogens, oxygen has 6, 4 plus 2 plus 6 equals 12. So I can have 12 dots. Now carbon's going to be our central atom, hydrogen is going to bond to carbon, oxygen is also going to bond to carbon. Okay, this is kind of a funky little challenge of a shape. So the next step is to single bond everything. And then give everything a full octet. All right, so I've single bonded everything. I've given everyone a full octet. Reminder, hydrogen can only bond once. It can hold up to 2 electrons. And now if I'm counting, I have more than 12 dots. So I need to make a double bond, okay? To make a double bond, I'm going to erase and move, all right? So I'm gonna erase, okay, a pair of dots from the 2 atoms I'm making a double bond between. I cannot make a double bond between carbon and hydrogen, so my only option is between carbon and oxygen. So I'm going to erase this one lone pair, not lone pair, that's the wrong term, this one pair of electrons from that carbon, and then I'm going to erase a pair of electrons from the oxygen, and I'm going to place a double bond. At this point, okay, I have now used 12 dots. All of my atoms have their octets. They're nice and happy. We can move on to the next part. So now we have to find if the bonds are polar or not. We look at each bond separately, okay? I have 2 types of bonds. I have a carbon to hydrogen bond, and I have a carbon to oxygen double bond. Now, single, double, triple, that does not affect the polarity, all right? Does not affect the polarity at all. So I'm going to go and I'm going to find my electronegativity differences. So I'm going to have my bright green polarity handout. So the C to the H bond, I have 2.5 minus 2.1 equals 0.4. That is non-polar. All right. So these two bonds that I'm pointing arrows to are non-polar. That means I don't need to add partial charges. I do not need to add dipole arrows, okay? Because those two bonds are non-polar. Now we're gonna look at the carbon to oxygen electronegativity difference. Oxygen is 3.5 minus 2.5, 1. So this is polar, okay? Because I have a difference of 1. Oxygen is more electronegative, okay, with a value of 3.5, which means oxygen is going to take the partial negative charge, all right? So carbon has a partial positive charge, all right? And then I'm going to draw my arrow. So remember, I have that funky tail that looks like a plus sign, and my arrow is going to point to the oxygen. All right, so your homework or your practice is going to be drawing Lewis dot structures, all right, and determining the polarity. So if you don't have a polar bond, you don't need to add partial charges to those atoms involved in that bond. If you do have a polar bond, you need to add partial charges and this dipole arrow, okay? All right, so why are we talking about polarity? It's going to be pretty important after we learn the next topic, but polar compounds and nonpolar compounds have some different properties. So again, polar compounds, the electrons are unevenly shared. They're soluble in water. So soluble means it can dissolve in water, which is pretty important, okay? If I'm mixing a certain chemical with water, I want to know if it's going to dissolve or not. They usually have higher melting and boiling points, okay? And when the polar compound is mixed with water, it's usually conductive, right? Not as much as ionic compounds, but it can be conductive. So some examples of polar compounds you see every day. Isopropyl alcohol, okay, that's 70%, means that it's 70% isopropyl alcohol, and the 30% is water. We also have ammonia, NH3. This is also usually mixed with water when you buy it from the grocery store. Lastly, we have properties of nonpolar compounds, okay? Nonpolar compounds, electrons are shared evenly, okay? They are hydrophobic. So what that means is not soluble in water, okay? They don't like water. They have poor conductivity, and they have lower melting and boiling points. So some really good examples of nonpolar compounds are olive oil and butter, okay? You might have learned about fats or lipids in biology, okay? Those are when we have those carbon chains and we have just carbon to carbon bonds and carbon to hydrogen bonds, okay? So these are super nonpolar, okay, because we've already seen carbon to hydrogen bonds, nonpolar, carbon to carbon bonds, nonpolar. So this butter and olive oil is just a good example of what we see every day, okay? So that is the end of this video. You should complete the practice worksheet and turn it in. There should be paper copies, but if you cannot find paper copies, the online ones are on Canvas.